Science Festival. It's been really good to see all of you again. Like David said, this is a second part to our sandbox session. Last week I had I spoke about Graphcore, the intelligence processing unit, that was that was last week. But today we'll have a hands-on workshop on how you would be able to run BERT fine-tuning on the Stanford question and answering dataset, train it on our intelligence processing unit, get access to the IPUs through our cloud partner, and finally have an API endpoint running on Hugging Face Model Hub. So I'll just quickly have a recap of just a quick talk through about me. So I'm Tim, so Director of Developer Relations from Graphcore, and who we are. So we our mission as Graphcore is to enable the innovators, you data scientists, AI researchers, ML engineers to provide the innovators both the hardware and software to help you find the next breakthrough in AI and beyond. And how we've done that is by creating our own processor we call intelligence processing unit that is built from ground up to handle AI workloads. And just recently, we have created the world's first 3D wafer on wafer processor that would enable us to build ultra intelligent machines that can handle up to billions and trillions of parameters. And I've discussed before that we have grown. We have a very mature software stack, software ecosystem. This means we have integrated to software libraries, development tools that are very familiar to you data scientists and AI practitioners. So nothing new here. We have our own SDK as well for those who want to code on a lower level. We call them the Poplar. But from a frameworks level, your notebooks, frameworks, PyTorch, TensorFlow, and recent integration with third-party software tools like weights and biases, HuggingFace, all of those would work out of the box. Aside from that, we have a growing tutorials, example and code examples. We have our model garden, which consists of around 50, as it stands, 50 example models that you can take and run and give it a try. And it's growing every time we release. Every time we have our SDK release cycles. So I'm going to be fine-tuning BERT for the question and answering dataset. Just a quick recap on how our recent submission to MLPerf VU 1.1. Our results for BERT are best in class. It's the fastest single host server BERT training, as it's shown here in our recent recent result. We have a deep dive on how we have achieved that through optimization and our performance optimization techniques. We have a deep dive of that, a separate document and YouTube video. Aside from that MLPerf submission, because of the most recent wafer and wafer processor we call BOW, that actually increased to we have actually achieved 40% more, a 40% improvement on our MLPerf submissions. So yeah, watch out for the next MLPerf submission where we will be using the latest BOW processors. So that was the quick recap. I think we could jump into the our hands-on demo. Like I mentioned earlier, we'll be using, you could visit this this code here in this link. Will bring you to so one of the repos where we have the code. Here you can sign up in Spell. We're going to be using Spell, which is our cloud MLOps partner, where you could get free access to IPUs and Hugging Face in some of our developer resources. Let's just jump onto that. Yeah, so that link would take you to one of the this demo in a box repo that would contain a Jupyter notebook that has our code for today. It would also contain like your basic instructions on how to run this tutorial on say a bare metal server or another cloud service provider where you could get access to IPUs. But for this hands-on workshop, we would want to go through the spell route. So like I mentioned earlier, Spell is our cloud MLOps platform. Make sure if you go to this link, sign up, you would get into to a wait list where you get eventually yeah, it doesn't take long to get some approval to get access to IPUs. That gives you 6 hours of free access to pod 16. And from there, once you've signed up and signed in, logged in, you can just click this run and spell button that launches you to our work to an workspace creation workflow. For example, here is some of the fields have been pre-populated. Let's just do that. And you can see what happens here is that it preloads the workspace with a code. You can select whether you want to run on a Jupyter Lab or a Jupyter Notebook environment. So let's just use Jupyter Notebook one. Here you can select IPU pod 16 as the machine type and preloads the Docker image. So that takes it from our official Docker Hub organization. So Graphcore releases the SDK and the framework on top of the SDK. We have a few images that are catered towards production level like production images. We have production images where it's more slimmer and minimal. That's easier to extend when you want to run in a deploy. You want to deploy in a production environment. But in this case, we also have more ease of use type of images, wherein you have your Jupyter Notebook, your usual data science experimentation tools and libraries pre-installed. There are different OS support in the Docker Hub. You can visit that as well. And aside from these, so Spell allows you to do install other pre-installed pip packages or other libraries. And sorry about that. So dataset about data sets, we have made data sets available. So in Spell, you have available data sets there so that you can run our tutorials and examples without having to download those publicly available data sets. So as much as we can, we have made it available here, and then just mount it. So you can also set your timer to to auto shut down this workspace. Um, and in this case, let's give it some like maybe an hour or so, but we wouldn't take that long. So creating that server, what it does is just preloads the image that contains the SDK, and spins up this notebook environment. So that's what's going to happen. Okay, that ran quite fast. So we'll go through, I won't be running the code. Um, we'll just walk through the code right now, but all of these has been pre-run before. The output in the cells would be what you would be expecting to see. Like I've said earlier, what we're going to do is take BERT pre-trained weights from Hugging Face that is trained on a Wikipedia data set. Take those model weights, fine tune it on a squad Stanford question and answering data set, and then we'll run inference. So as you can see, we're just using our standard deep learning libraries, for example, transformers, Hugging Face data sets. What we imported here is PopArt and PopTorch, which consists of the packages that would allow us to run on IPUs. So after that, getting the data from Hugging Face, we're gonna use Stanford question answering data set. So it's a reading comprehension data set consisting of questions on a set of Wikipedia articles. So what a single data point would look like is a context passage, a question, and then a ground truth, which is the answer. So the ground truth would look like the actual text passage and the position of that passage within the context. So what this does is just using datasets library, we're just it's going to automatically download a public dataset found in the Hugging Face hub and load it into your Python object. So these datasets come pre-split into training and validation, so it's easier to sort of benchmark it against other models. And as I've shown earlier, this is the context. Here is a question and your ground truth, which is the passage and the position of that text. So after that, we need to, in order to, I think another thing that I wanted to mention is that what this does is actually, we're just, it means you're able to use everything that's in out of the box. Like there's nothing different. It's Hugging Face data set, so you're open to using easily using and accessing those data sets. And in order to run our models, train our deep learning models, we need to convert these texts into numbers. And what we're using is we're using transformers, BERT tokenizer, for example. So that what that does is just encodes our text into numerical, a list of numbers that gets fed into our deep learning model. And in this case, what we're doing here is that um, we are encoding, using BERT tokenizer, we're encoding our text into a list of 32 integers, as you can see here. And once decoded, you can see that this that the decoded version consists of the question and then the text, followed by padding. So we've set it to have a maximum length of 32. So once encoded, it's got a list of 32 integers encoding the tokenized version of our text. And in order to run, we on our training data set and validation data set, we want to featurize the entire data set, and we can import a helper function called the prepare train feature. It comes from Squad preprocessing library, and what that does is it loops through the entire data set and tokenizes them. So now that you have the data set prepared, we need to, here we want to discuss like how we can parallelize models in the IPU. As I've mentioned in my previous talk, so there is a, the IPU is unique because of its fine-grained parallelism. And one of the key parallelism principles that you would be encountering when you're coding in IPUs would be model parallelism and pipeline parallelism. So model parallelism basically is partitioning our model and splitting them up into the different devices, as we can see here. So so for example, our BERT-Large model has 24 transformer layers, and splitting them up, splitting the entire model across different IPU devices would look something like this. So wherein we're assigning the embeddings on an IPU device 0, for example, and then spreading out the 24 transformer layers across different IPU devices. So here we're splitting it over 8 IPUs, wherein 3 of the transformer, for example, in IP1, you have 3 transformer blocks, so on and so forth. And so that's your model parallelism. And pipeline parallelism means, so this is where this is the part wherein you're executing different data sets, micro batches of data across the different devices. So if we're to look at this this vertical column as a time step with these rows as the IPU devices. If we look at the journey of a micro batch of data across the pipeline, on the first time slice, you have the first micro batch running a forward pass on the first IPU device, which consists of the embeddings into encoder layers. And once that forward pass, that calculation finishes, it then gets passed to the next part of the pipeline, which is in the second IPU device, and then so on and so forth. with the other IPU devices being fully utilized with the next micro batch, up next on the first IPU device, and making sure that we are fully utilizing the entire pipeline and minimizing idle time across the devices. So as one micro batch goes, does forward pass through the entire pipeline, it then does the backward pass and accumulates gradients across on its way back along the pipeline. So that is your model parallelism and pipeline parallelism. Another way to speed up the runtime is to do data parallelism. And as we can see here, there's only 8 IPUs that are being utilized, we currently have like 16 IPUs on this device that you're able to run on Spell, and our pipeline is currently 8 IPU long. We can replicate this pipeline, feeding 2 different micro batches to the device, effectively having double the mini batch size. So we call this configuration 2x8 pipeline. So basically 2 of these 8 IPU pipeline. So other things that can be done in order to like fully utilize the IPUs is covered in our performance and optimization documentation. We have also covered, we have a separate video talking about how we have achieved our MLperf numbers. So some of the optimization techniques, such as recomputation checkpoints, wherein you're playing around with trading off with a trade-off between saving optimizer states in memory versus utilizing the speed to recompute the flop expenditure. Rather than saving it in memory, you're doing recomputation every time, because you wanna in these scenarios, you're not you're not having to get memory. Well, you're basically having a trade-off between having a saved memory and faster arithmetic calculations. So the other techniques are covered here, and how that looks like in code basically is we extend, we subclass the Hugging Face BERT for question answering model, and then implement a parallelization method that does the distribution of each layer into the different IPU devices. So this is one of the way wherein you are taking if you're gonna take your your model and port it into IPUs. So we have been working with Hugging Face in order to create a library. We call it the Optimum library, which helps you use transformer models out of the box. So you won't have to do, you won't have to implement this. But if you were to take this route, if you have a bespoke model, so you would have to follow this approach. Here we are seeing how we are assigning each layer into an IPU device, let's say here the embedding layer, and then looping through the different transformer blocks in the different IPU devices, and implementing each at the end of it, the output layer on the final IPU device. So that is just the implementate how it looks like in code when implementing this model pipelining. Yeah. So now that that's covered in your model class. So what we're doing here is actually downloading, instantiating the model object by downloading a model checkpoint available in Hugging Face Model Hub. So as you can see here, since we have subclass the BERT transformer, BERT for question answering transformer class, those checkpoints that are available in Model Hub will work out of the box. So here, what it does is downloads the checkpoint and then loads it into, instantiates it into our model object. And once we run and instantiate that, we're able to see that, and once we call model parallelization, it assigns the different layers into the different IPU devices. And in this scenario, in this example, we're calling the half method to cast all model weights to half precision. So we'll be running training in half precision. So once you have that model implemented, here are the ways on how you could set the runtime configuration for the training. So we will use a global batch size of 256, a micro batch size. Earlier we have shown the pipeline execution to have a micro batch size of 2. The data parallelism that we have shown earlier to have a replication factor of 2 as well. So it is this 2x8 pipeline, and how it's set is by defining this IPU training options. As you can see, I think what I just wanted to cover here is that, you know, this is how easy it is to set these runtime configurations. So for example, this is how we would set or enable a pipeline execution strategy. We want to enable stochastic rounding since we're training in half precision to minimize quantization loss when operating in half precision. And other things like the replication factor that I mentioned earlier in order to do data pipelining, executing enabling executable caching. So once you have compiled the model, you don't really need to recompile them, you know, making your model training faster, so you won't have to always recompile the model. So the other optimization concepts discussed in the optimization and performance optimization guide would be covered in this section. You would want to implement them here, and I suggest you check them out. So So those are our runtime configuration options. So the next section would be how you would implement your training loop. So a few things that I think I'd want to highlight is that in order to load our data into the IPUs, we're just using a drop-in replacement of PyTorch data loader. So it's just an extension of the PyTorch data loader with specific options and asynchronous execution that really suits the IPU. So this is the PyTorch is our framework that extends PyTorch PyTorch library. So aside from PyTorch data loader, we will be using a PyTorch Adam W optimizer. So again, it's the same. It's the same as the PyTorch optimizer. So we have also made available other optimizers in PyTorch that has the additional configuration and features that would run when you're running an IPU. So now that you have created your optimizer, we want to be able, what we're going to do is pass the model that we have created in the first section, the runtime configuration, and then the optimizer state, and pass them to PyTorch training model. So the training model handles the forward pass, backward pass, gradient accumulation in the IPU. And here we create the training loop that does which tells the training model to do the forward, backward, and gradient accumulation across different epochs and loops through the epochs in the training data set. So now what's going to happen here is once you've run this, this takes around 9 to 10 minutes to fine tune the model. Once that's done, you can save the checkpoint. This is quite useful because we want to be able to either load from checkpoint or in our case, in the future, upload it, share it, and put it in inference. Just take note of that. This is gonna get saved here. We'll use it later on to upload it to Hugging Face Model Hub. And I wouldn't go through the validations pipeline that much, but one of the key difference we have here is that we don't need stochastic rounding for the validation because you're not updating the weights when training, so you don't need to worry about the numerical stability. And it's going to be a little bit more simpler, and you'll be using instead of training model, which we have used here, we'll be using an inference model later on in the validation and inference pipeline. So again, so just moving forward from there. So here's the bit wherein we're using inference model, and then passing the model and runtime configuration, and no optimizer state necessary. And once that's done, we can see here that we have, using this code, we have achieved 84.7, which closely resembles the reference model, BERT-Large model, F1 score of 91.1. But what I wanna show as well is that with this, now that you have like a trained model with a model checkpoint that we have saved, we have validated that it's trained properly. This section would be how you would reuse this model checkpoint, wrap it in a serving harness. If you wanna have an inference server, let's say. So that's one part of it. But I want to focus on how you could use it, how you could leverage Hugging Face Model Hub. So from here, for example, if you log into make sure that you're logged into Hugging Face, you have your account. What this does is it brings you up to this interface that asks you for a token, so that you can push directly your model checkpoint, the one that we have, like the output of the training, into Hugging Face Model Hub. And once you have that push into Hugging Face Model Hub, what that would look like would be something like this. Sorry, actually something like this. So these are the models that are available in Hugging Face Model Hub. Let me just pull this up. Let's open one of the model cards. So what it does is pushes the model checkpoint and the accompanying config files, the vocab text. And what that does is it allows you to run inference requests on the model card. Yep. So I you just have to replace it with your own username. What does so actually this is the example of when I ran it. So there's also a running so this is the output of when I ran it before this demo. But what that does is makes the model available for serving. Okay, that's one. There's a few examples. And because it's up there already, you can hit this API endpoint by just sending a post API request to it. Let's try opening up Postman, and I have pre-filled this, so it could be. Let's give it a look. So here it's Graphcore, BERT-Large encased. You can try it yourself on this official Graphcore model card by sending this JSON payload with question and context, like we've sent. Yep. Okay. So this answers one of the samples I had about a previous event. So this is a bit malformed, but Okay, so this sends a request to my API endpoint. BERT Fine-tuning demo, is that correct? BERT-Large, it's called BERT-Large Encased Squad. Yep, and yeah, and there you go. You have a working API, like an inference API out of the model you've trained. Yeah, so that's it for today. That's my walkthrough of the BERT fine-tuning demo using IPUs on Spell and Hugging Face. And these are the links to what I've shown today. The code is available here in this link. You could sign up in Spell, get access to IPUs. There is also, I mentioned earlier that we have partnered with Hugging Face to have, so you won't have to implement the transformers manually. If I had a run earlier, but basically it's quite easy. Once you have Hugging Face installed, the Optimum library installed, it's just one line of code, and then you're able to one command, and you'll be able to run and use the model checkpoints out of the box, just like that. So yeah, that's the demo I had for today, and I think we can open the floor for discussion.
Amazing, Tim. Thank you very much, sir. Thank you very much. I must admit, anytime anyone's running a demo, I don't care how often you run a demo, it still makes me sweat. And that was like super professional. So thank you very much for that, man. Really appreciate it. What I might get you to do, actually, we've put some of these links into the chat already, so I might get you to stop sharing your screen, and then the people at home will be able to see us slightly bigger, which I'm not sure if it's a good or a bad thing, to be honest, but they'll get to see our faces a bit bigger. So there we go. In terms of the Q&A, we have got one that's come in from the audience at home. I've certainly got 3 or 4 myself. So I'm going to crack on with a few questions. If anyone has any, just stick them in the Q&A, and we'll do our best to pick those up for you. I guess just kicking things off from my side, I must admit, watching it, I was very keen to find out, what's the main difference when optimizing your training and validation pipelines when you're working like this.
So the validation pipeline doesn't so one of the configs that you have to set is you don't need like stochastic rounding, because you're not updating any weight. So that's one. Like you're using the inference model instead of training model. So there's that section there that shows how to use the inference model instead. Yeah, and then you could have like you could use like fewer IPUs to run inference and validation.
Perfect. Thank you very much, man. Thank you also to Eleanor and Stanley for dropping those questions into the Q&A. So if you want to open up the Q&A, we'll be able to read along at the same time. We've already seen actually one of the questions has been upvoted. So if you spot a question that you like the look of, people can upvote it as well if you're watching along at home. That top question there from Eleanor is specifically, is the inference API using IPUs?
So the Hugging Face inference doesn't use IPUs. So I think it's running on CPU. I have made the in the code that I have shown, the inference bit would be using IPU. So that's why you need PyTorch inference model because that handles how you would run inference in IPUs. So yeah, you could check out the notebook on the inference part and run it in IPUs. Mm-hmm.
Perfect. Thanks very much. And Eleanor had also followed that up, but just to sort of double check, you may have just answered that as well. But Eleanor was also asking, can you quickly recap what the purpose is of PopTorch and Optimum Lib? So is that the reason there?
Yeah. So PopTorch is the library that allows you to run your PyTorch methods. It's PyTorch in IPUs with IPU support that works with the IPU, the Poplar SDK. So that, like, for example, the data loader, the optimizers are like stand-in replacement from the standard PyTorch, so that you can run them in IPUs. So for example, the training model object, you pass it the model that you have created in standard PyTorch, and then it handles the forward, backward propagation, and gradient accumulation within IPU. So it has that additional, it's an extension, the extension to the standard PyTorch framework. The Optimum library, so the Hugging Face Optimum, allows you to run the model checkpoints out of the box from Hugging Face Model Hub. So the last bit that I quickly shown, wherein I just like had a run command, but what it does is that you don't have to implement the training loop. You don't have to have set up the model partitioning that I have done in like the first part. It just takes the model checkpoint and then runs it in IPUs. So it's a quick, just import and run.
Perfect. Thanks very much, Tim. I'm going to tackle this question here from Azucena. They're asking, how do you decide the numbers of IPU for training?
Yeah, so it depends on the how large your model is. So there is so within a processor, within the IPU, you have like 900 MB in processor memory. So there is like a trade-off on like how much you can fit within a single IPU. So that's for start. Like, would you be able to fit it in the IPU's memory? If not, then you start splitting it out into different layers. And then if you can, now that's where it starts to get interesting, because then how you're going to distribute, like the model parallelism will depend on how much like parameters could fit in an IPU, and then replication as well, right? Like how many the data parallelism that we've discussed earlier. It sort of helps you. You want to be able to utilize as much IPUs as you want. You want to harness the parallelism involved there. So yeah, so initially it's like fitting it in the model, and then you have some trade-offs between like what is like accessing memory in say streaming memory, which is outside the in-processor. So those are two different memories where you could utilize. So there's that communication. Yeah, it's the cost for communication versus the cost for calculation, for example. Yeah. Communication and accessing memory, for example. So
amazing. I think for me, that, if I'm honest, that's the most appealing part of all of it. You having to be a bit closer to the hardware and understanding the underlying architecture. And, you know, it used to be the same, you know, be it with discs or whatever back in the day when things weren't quite as quick. You had to work out what you're doing. So yeah, I love to hear that. I'll jump onto the question at the bottom if you're following along in the Q&A from Stanley. Stanley was asking, how do you decide whether half precision should be used during training?
Yeah, so a lot of these, so AI is quite, they've seen that half precision works quite well with the AI models, right? You don't, it's not the penalty of going with a less precision is not as drastic. And then actually we have that stochastic rounding to even minimize the effects of you know, the numerical stability, because when you're doing downsampling to have precision, so there's obviously going to be quantization loss from there. But yeah, so obviously you're going to have like a speed up by cutting the by operating in half precision, basically. So it's pretty quite common nowadays, especially when you're trying to go with bigger models. You want to speed up the training. You want to be able to fit more within the constraints of an IPU device, within one IPU or multiple IPUs. So I think that's the trade-off there.
Okay, perfect. Thank you very much. Question there from Eleanor. Eleanor's asking, does Graphcore work with pre-seed or seed startups? I'm not 100% sure whether, you know, if she's asking if there's discounts, ways to get involved, or whether she's looking for funding, perhaps. I don't know, maybe Graphcore could invest in her business. But yeah, can you tell us a bit more about how people can, you know, start using, you know, this technology?
Yeah, the most I think get your self up and running is the Spell Cloud platform, where you don't even have to speak to someone from us. Just log in and try it out. I think there's a question about the IPU trial in Spell. So that is like you have a maximum of like 6 hours running some on that platform. So to be able to experiment like this BERT fine-tuning model, for example, it's like takes 30 minutes to run, to click through it. So and you can take some of the there's like 50 readily available examples that we have. So that's one. We have trial. We do work with, of course, like very those who have needs for an accelerator for AI workload. So you could reach out to me. We have our you could visit the website graphcore.ai. We do have like an evaluation period trial where we try to help you out, also identify like how the hardware is going to help with your workload and accelerate it. So yeah, so that's one. We also have our cloud provider. So we have what we call Graph Cloud, which is cloud access to IPUs, wherein you could have the trial in Graph Cloud, and then from there assess how to move forward. We have academic program wherein we work with researchers who have like potential use cases for IPUs. We've mentioned that like we we believe that IPUs are going to be very strong for like large models, for sparse computation, for graph. So yeah, if there is a form that you can fill out to send a proposal on like how we could work together, publish a paper, or work on something.
Yep.
So
I love to hear that. So basically, slide into Tim's DMs is the answer to that one. Talk nicely to Tim. So I'm a little bit conscious of time. I think I'm going to take one more question, if that's all right with you, Tim. We are just slightly creeping over time, so we'll take one more question and then we'll draw things to a close there. So we'll take that bottom question there, if you don't mind, Tim. The question there is: did you train the model with different layer partitions before finding the best model? Could you advise whether partitioning certain number of layers can impact the results? So can you tell us a bit more about that, please?
Yeah, so yeah, there's some experimentation involved around it, because like as much as possible you want to have like a load balance of like the sizes of layers that are spread out across the IPU devices. It's gonna be impacted by that, because if you're front loading the IPU devices, yeah, so it's there's also that load balancing type of activity, design activity, so to speak. And did we train the model with different layer partitions before finding the best model? I'm not quite sure, but we can take off that question offline. But this is one configuration of training the model. It could be split. The model partitioning could be split in different ways, which would affect the performance. And in our MLPerf video deep dive, actually it's shown there like how the splitting actually was done, and it's an optimization problem thing with this once you go parallel, right?
Perfect. Awesome. Well, we will draw things to a close there, actually. So thank you very much once again, Tim. It's been nice to have the two sessions like week to week. So it kind of really felt like we told a bit of a story, went on a bit of a journey, and to pull it together there with the demo at the end is fantastic. And personally, I've loved learning more about Graphcore as well. You know, as mentioned at the start, I do love finding out about these very innovative companies, and particularly in the hardware space. You know, it is a little bit more specific, isn't it? So yeah, thank you for taking the time. Definitely want to give a shout out to Graphcore as well. You've been absolutely great partners. I know Kelly's watching along at home as well. She's jumped in the chat a couple of times. So thank you very much to everyone from Graphcore. I would definitely hope that you all go out and check them out, check out the website, follow up on some of these links, and hopefully become avid Graphcore users as well. So that would be great. But as I say, we will draw things to a close. I'll hand over to you, Tim, for the last word. And yeah, hope you've enjoyed it. How did you find presenting at the Data Science Festival?
Yeah, it's pretty cool, and also it's one thing to present, and also the follow through. Like I've been speaking to a few people who's like very keen to sort of a few people slid into
the DMs. I love to hear that. I love to hear that. So hopefully there'll be a few more today, and I'm sure we've been talking to Graphcore for a couple of years now, so I'm sure we'll do something else with you guys at some point, and yeah, we'll have you or someone else from Graphcore back at some point in the future. But thank you very much, Tim. Thanks very much, Graphcore, and thanks to all of you at home for joining us today. We'll hopefully see you all very soon. Thanks very much. Bye-bye.
Thanks. Bye.